Okay, today we are talking about solving systems of equations. A system of equations is multiple equations with multiple variables, or sometimes we'll call it equations with unknowns. Variables tend to be unknowns. And what we're solving when we find this, if we're talking graphically, is a intersection point. Those are two lines. We will also solve nonlinear things. There's two intersection points now for this. And right now I'm starting with two equations with two unknowns. That's where we're going to start, but you can move this to 20 equations with 20 unknowns, and you can still solve it. It'd be a really big pain to do by hand, but we'll show you how to use matrices to do that. And I believe we did a little bit of matrices for solving these in Algebra 2. So this is section 7.1. And there we go, solving a system of equations. So here I've got two equations, both in standard form. And we're going to solve these by substitution. There are multiple ways to solve this, but we're going to use substitution here. Okay. So I'm going to take this first equation, and I'm going to solve it for y. That means I'm subtracting 2x from both sides. And I'm just putting it first. So I did minus 2x on each side. And I put the x first because that's slope intercept form. That's kind of what I'm used to. I need it to be positive y. So I'm going to get y equals 2x minus 10. So method one is substitution. I forgot the equals here. Okay, clean that up a little bit. And sometimes you'll see the equations put in a bracket like this. That wasn't a very good one. It's a set brace. Not always. Actually, our book isn't, but that's pretty common. So I'm going to take my second equation then, and I'm going to plug a 2x minus 10 in. And you should have all done this several times before. This is substitution. I'm going to distribute. I will add 20 to both sides here. And I get 7x equals 21. I'll divide by 7. That was supposed to be a 7. And I get x equals 3. I am not done when I get x equals 3. I must solve for y. The easiest equation here is the y equals equation. It doesn't matter which if you use either of the originals, but I prefer to use the y equals equation. And I plug in x. 2 times 3 is 6, minus 10 is y is negative 4. And it's fine if you write your answers. It's got to be a 4, not a 9. It's fine if you write your answers like this. It's also fine. I don't know what the answer book does here. Right, as an ordered pair. That was example 1. Example 2 is going to be a nonlinear system. The first equation here is a line. The second one is not a line. xy equals 300. Well, I'm going to solve this for y. Doesn't really matter which one I choose. And I'm not going to do it how the book does it, which the way they did it was fine. I'm going to do it different. You can look at the way the book did it. They solved the top equation for y. Plugged in. So I'm dividing both sides here by x on the bottom one. I get y equals 300 over x. I'm going to do it this way because it's a good example to review some solving tricks from Algebra 2 and a little bit earlier this year. So now I'm going to plug in for y, 300 over x. To solve this, I need to get my x up. So I'm going to multiply everything by x, giving me 2x squared plus 600 equals 100x. Now I'll set it equal to 0. I can factor out a 2. And multiplies to 300 and adds to 50. Um, hmm, we're not going to get that. So we're going to have to use the quadratic formula on this. I can factor out the 2, though. That does mean make it a little bit smaller numbers. 50 plus or minus the square root of 50 squared is 2,500 minus 4 times 1 times 300 over 2. 1,300 over 2. And we're going to get these two values for x. Nine, 7, 2. So, yes, I should plug them both back in to get y. Um, and again, I'll use this y equals equation that I made here. This is kind of nice. I don't even need to. Oh, hey, that's the other x. And when I swap them, I get 43.027. So I have two solutions to this. And part of this works because they're exactly identical. They will not always, both solutions won't necessarily give you x and y, but this one it does. And those are my 2 points of intersection. Okay. Solving another nonlinear system algebraically. Again, this is nice because they're both equal to y already. So I can just set them equal to each other. I'll subtract 3x from both sides. Oh, this is going to be nice. This will factor. I'm going to factor out my greatest common factor, which is x. Now, x squared minus 9 is a difference of perfect squares. So I can factor it like that. Now I know 0 is going to equal any of my factors. Quick review of solving by factoring. So I've got 0 equals x, -3 equals x for that one, +3 equals x for this one. So I have all three of those as answers. That is example 3. So those are substitution method. Very useful. There's also the elimination method. Which we're going to take a look at this one. Oh, I suppose I need to write what it equals. Okay, so elimination method is a very important method. So again, I'm going to use this elimination method, which means I'm going to get a variable to cancel out. And I'm going to go with x. When I add them together right now, it doesn't. So I'm going to multiply the bottom by 2 and the top by 3. So I get a 6x and a -6x. The top one becomes 6x plus 9y equals 15. The bottom one becomes -6x plus 10y equals 42. Now I'm just going to add these two equations together vertically. 6x plus 6x is 0x, so that's gone. 19y equals 57. And divide by 19, and I get y equals 3. I'll take one of my original equations and plug that in. That's 9, so I'll subtract 9 from both sides. Get 2x equals -4. Divide by 2 and get x equals -2. So my solution is -2, 3. Okay. Example 5 is another elimination problem. Okay, so I'm going to multiply the top one by -2, so my x's cancel again. And this one I can just write underneath. And when I add these together, I get 0x plus 0y. Oh, that's 0. That whole side is now 0. And 4 plus 4 is 8. That is not true. No matter how hard I try, I cannot make 0 actually legitimately equal to 8. That means this has no solution. If you do this, your x's and y's cancel and you get 0 equals 0. That means that they're the exact same line. They are, yeah, different forms of the same line, so there are infinitely many solutions. So what this looks like is something like this. They're parallel lines. I don't know exactly. I'm not going to go through the work to convert them right now. But they are parallel lines. That means there are no solutions. Now, here's example 6 is an infinitely many solutions one. So I'll go through this really quick. So multiply my top one by 3, giving me 12x minus 15y equals 6. When I add them together, I get 0 equals 0. Those are the exact same line, just written in different forms. If I had chosen to multiply by -3 so stuff didn't cancel, I would have gotten the bottom equation by multiplying the top one. Okay. Estimating personal expenditures with linear models. So if you take a look in your book on page 573, they have some data here. And they've got year versus dentist and health insurance. So common expenses. So we're going to go to our graphing calculator. And we're going to graph this. So I'm going to take my data, I'm going to put it in my list. Nope. I don't want to go second list, I want to go stat. Edit. I got a lot of these to clear. And I'm going to clear them all because I think I might need them all. And remember to clear, you scroll up to the top, hit clear, scroll back down. So they say to use x equals 0 as 1990. That means 1995 is 5, 8, 9, 10, 11, 12, 13. So 2003 being 13. 45.4, 54.1. These are in billions. Okay. So first thing we're asked to do is find a linear regression for the US personal consumption expenditures for dentists and health insurance and put them on the graph of a scatter plot. So to find a linear regression, notice that L1 is the X for both of these. So we're going to use stat, calc, linreg, AX plus B. I need L1 here and L2. I don't know what I did last, but it wasn't those. And I want them on the scatter plot, so I need to make sure I put this in function y1. And there is my scatter plot. Let's make sure it's set up as a scatter plot. It's not correct here. L1 versus L2. Y equals has that blue, that's good. Zoom, stat. I didn't turn my stat plot actually on. There, now it's on. So now we can do some stat, and we can see our equation for our line. We're going to do the same thing with the other data. Nope, wrong one. Stat, calc, linreg. This time I'm doing L1 versus, I keep hitting the wrong buttons. Stat, calc, linreg, L1 versus L3. And I'm going to store my regression equation not in y1, but in y2, because I still want the one that's in y1. I'm going to set up a second stat plot. Turn this one on. It's not L3 versus L4. It's L1. That's a common one to use, but L1 versus L3. Let's redo my zoom so it should now hit both of them. So we can see that the one is growing faster. So use the models to estimate when the US personal consumption expenditures for dentists will be the same as health insurance and the corresponding accounts. So we actually have to adjust our window to see this. And actually, if we look at the graph, we can see that it's actually going off the left end. So it's into the negatives, most likely. Um, so I'm going to take my window X. Let's go to -20. Actually, I need to use the negative button on the calculator. Scale, let's make that 1. Y min. Um, let's still make this -100. Y scale 10. Now let's try graphing. And I do see an intersection. So another way to solve these, you could have taken those equations out and solved them by hand. But another way to solve these is with the graphing calculator to graph them both. And remember, I can find intersections in the second trace of the calculate menu. So second function of trace, calculate, intersect. The first curve, it's nicely showing as blue here. I like the colors. Second curve, if you can't see which colors are, you have to scroll far enough away that you can tell when it's switching curves. Guess. Get it somewhat close. It matters if you have multiple intersections, and you will sometimes. So we get -2.56. That means it's in the year -3, which doesn't sound very meaningful, but 1990 was the year 0. So the year -3 would be 1987. These were equal, according to these models, in the year 1987. Yes, that is into the past. And according to these models, they will never be equal again because the health insurance, or the red line there, is growing faster than the dental amount, and the dental amount is smaller and it's growing less quickly, so it will never catch up. Okay. There are lots of applications for these. Using technology like a graphing calculator is really helpful sometimes for finding the intersections. Can make it a lot faster. When you're doing this in class, make sure you follow the instructions for how it tells you to solve, because I do expect you to be able to solve by both substitution, elimination, which is sometimes known as linear combinations. Linear combinations is because I'm adding linear equations together. And then also potentially solving by graphing. So all of those methods are in play. If it's graphing, you can use your calculator. If it's not, make sure you follow the instructions. And when you take the quiz on this, you will have to do both. Okay, one more example. We're going to look at example 8 and apply this to another problem. Niebach Manufacturing determined the production price of new tennis shoes should be generated by the equilibrium point for the system of equations. Well, that was nice. They gave you the system of equations. They didn't make you write it. Sometimes you will be expected to write the system of equations. Do I expect you to be able to write 2 linear equations? Yes, I do. Expect you to be able to read and find slopes and y-intercepts, or do standard form where you're applying. Standard form becomes really nice with a lot of these word problems, like 3x plus 2y equals 17. $3 per x plus $2 per y equals $17 total. How many x's and y's do you need to sell? if x plus y has to equal 5, for instance. A lot of things with word problems with these. Often there is one that is just, they tell you the total. X plus y have to add 84. That's a simple equation. That's the easy one to forget. It's the one that when I started teaching and was teaching these all the time, doing word problems, I'd forget that equation. I'd get the harder one, which usually isn't that hard. But I'd forget that one and be like, I need another equation. Okay. But this one, they happen to give you the two. And hey, which method do you think is easier? Well, I have p equals and p equals. Anytime I have a variable equals, it's usually easiest to do substitution, especially when they're both p equals or y equals or whatever the variable is, because I can just set them equal to each other and go about solving like I normally would. So I'm going to move my 5x and my 35. Give me 195 equals 25x. No, not 195. I need to subtract. I was like, this is going to give me a decimal, which is probably not really out of the reason. Subtract 35. 160 minus 35 is 125. I can divide by 25 and get x equals 5. I do still need to get p. So p equals 160 minus 5 times 5. Doesn't matter which equation I choose. I could have chosen either. P equals 135. So x equals 5 and p equals 135. The equilibrium point is 5. I think it's 5 pairs of shoes. 5 million pairs. And P is $135 per pair. Okay, that is section 7.1, Systems of Equations.